Okay, this video lecture here is to help you deal with some vertical problem setups. So as a reminder, I call it the vertical problem skeleton, consists of a free body diagram with arrows pointing up and down. The down arrow is FW, which remember stands for weight, and if you have enough information, the way you would calculate that is mass times the acceleration due to gravity, and then this arrow that points up is this thing that we call the applied force, which can come from a variety of places. And then we have two net force equations, one of which is F net equals the mass times the acceleration of the object, which I do want to highlight is different from the G, because G is always, here on Earth, going to be negative 9.8, but this acceleration here, I refer to it as the actual acceleration. This is the object actually picking up or losing speed in that problem. And then the other F-net equation is the concept that you add all of the forces together, and in a standard vertical problem like we have here, it is just the sum of these two forces in our free body diagram. Now, along with that, just as a reminder, reference frame, we need to keep in mind that anything acting upward is positive, anything acting downward is negative. And we could go one step further, and I'm going to do this in a different color as well. This A can be tied to our acceleration equations if we need to go there. It's kind of optional because it depends on how elaborate the problem is that they are giving us. And the last one is 2a delta x equals vf squared minus vi squared. Okay, so I think with what I have up here, this is everything we're going to need. So let's take a look at a particular vertical problem and see how all this ties in. Now, remember, I am not going to be solving this like doing the math for you. I am just trying to help you make the connections so that based on the information we're given, you could say, I can figure out how all the pieces fit together. Okay, so the problem that I have chosen to kind of go through is problem number 56. All right, and problem 56 says, as a protest against the umpire's calls, a baseball pitcher throws a baseball straight up into the air at a speed of 20 meters per second. In the process, he moves his hand through a distance of 1.5 meters. If the ball has a mass of 0.15 kilograms, find the force he exerts on the ball to give it this upward speed. So if you imagine a pitcher, being upset and then going to throw the ball upward, the idea is that from the bottom, it starts from rest, and then by the time he ends up letting go, it is moving at that 20 meters per second. So we have 20 meters per second. They give us 1.5 meters, and they have 0.150 kilograms. Now there is one, from my description that we just talked about of what's happening, there is one additional piece of information that they're not explicit about, and that is that the ball starts from rest before the pitcher goes to throw it up. So there is one additional value of 0 meters per second. So if we look at these pieces of information, the 0 meters per second is our initial velocity, the 20 meters per second is our final velocity, the 1.5 meters is the delta x because that is the distance, the vertical distance that the ball is moved through as it picks up the speed, and then our 0.150 kilograms is our mass. Now, one of the things that I would ask you before we get over into this particular part of the problem is, what are we actually looking for? Because the problem asks, find the force he exerts on the ball to give it this upward speed. And what most people look at when they're seeing this combination here is I see the VF, the delta X, and the VI. And they think, I got an acceleration equation, which is good. I can find an acceleration, and then I have a mass, so I could find the net force, and then, okay, I'm done. But that's not what we're actually looking for. Because when we come to the picture here, when we say, which of these forces is the force of the pitcher throwing the ball, the net force is what's left over when all of these forces are added together. That's this equation here. But when they ask for just the force that the pitcher exerts on the ball, that is, and I'll go ahead and circle this, that is the applied force. So over here at the beginning of the problem, I would ask somebody before we ever get started, what are we supposed to find? And I find a significant number of people just go right to Fnet and they end it there, and they're not interpreting the forces the correct way. So we are supposed to find Fa. So if we take a look at this, this is as far as I'm going to go. You need to use the right pieces of information with an acceleration equation so that you can calculate an acceleration. Then they give you the mass, which here would allow you to figure out the net force. And once you have this number, you can move it here. And because you are given the mass, you can figure out what the weight of the ball is, and that will go here. Now, as a reminder, the weight is acting downward, so it should have a negative sign. And then you use this equation to solve for the applied force acting on the ball. I hope that makes a little bit of sense for you in putting these pieces together. And maybe you could see why a lot of people get this wrong, because once they finish this first step over here with the acceleration equations and they find net force, they think, oh, I'm done. But that's because they're not interpreting the forces correctly for this problem. All right, so I'm not going to pick the equations for you. I'm leaving it there. All right, so I'm erasing this, and what I'm going to do next is I'm actually going to revisit I'm going to give you some hints on a couple of the problems, one of which is number 19. Now, the hints on 19, I am not going to have to go into as deep detail as we did over here for the prior problem. The thing about 19 that maybe people might find a little tricky is that you're just lifting some objects up, but the difference is that you have two separate objects. And what they are asking for is they want you to figure out, they call this rope segment AB, and they call this CD. And so what they want you to figure out is, we'll call it FAB, which is the force that this rope is tugging upward at. And then they also want you to find FCD. Now, I am summarizing here what we're looking for, because I don't want to go into too much detail. I just want to give you, hopefully, a picture that allows you to make use of our vertical problem skeleton so you can work your way to the answer. So first of all, some people would ask, why would the amount of force be different in the AB and the CD segments? And the answer to that is, if you pretend that you are this segment AB, you are responsible for not just 10 kilograms, but an additional 10 kilograms of mass to lift up. So when we are looking at trying to find FAB, what we can do is we can pretend we have a single object going through a vertical problem, but the mass that we use for that object is 20 kilograms because AB is responsible for both of these. But when we go to process this problem for, not AB, but for CD, CD is only responsible for that lower mass, and that lower mass is only 10 kilograms. So in the end, this is really the only trick, I guess we'd say, that you have to see through in order to solve problem 19. You can do the FAB segment simply by pretending you have a single mass of 20 kilograms and processing it using our vertical problem skeleton and free body diagram. And when you go to do the CD segment, you simply repeat the process, but you're using only 10 kilograms because that's the mass that CD is responsible for. And they do mention, I believe, that there is an acceleration, but because these are connected together, the acceleration they give you applies equally to each part of the problem. Because they don't get to move separately from each other, they are all moving together. So that's your hint on number 19, which I hope would help you navigate that one. Now the last problem that I'm going to give you a hint on, and this one's going to be real quick here, because I just have to identify a particular force that you're looking for, is problem number 75. Now for 75, this is about a person that's in a, this is a really lame drawing, who is standing on a scale in an elevator that's being moved upward here. And they want to know what is the reading on the scale. Now, there's a real detailed explanation we can get into here, but the main thing that you need to connect with is that the reading on the scale is equal to the applied force in our vertical problem skeleton. So this problem, it really has a lot of moving pieces on here, and you're going to have to make use of some of the acceleration equations. This is really a few different problems within one. But as you're processing this, you need to properly identify that what you're looking for in each case is the FA. And the second thing that I'm going to remind you of is our reference frame. Anything acting up is positive, anything acting down is negative. So you're going to need to be very careful about certain values that are given here and certain values that you have to calculate so that they properly have the pluses and minuses in place when you go to process this over here. All right, that's only 14 minutes. It's like a new record for me. So hopefully this has been enough of a hint and help so that you can work on the problems that I have left as part of the Google Classroom assignment. And then when I see you in next class, I'll kind of check in. I don't know if I'm going to do a whole bunch in class because I'm going to try and start to talk about the next type of problem, which will also have a free body diagram and some associated equations with it. So good luck, and feel free to reach out if you need to get in touch with me. All right? Take care.